In this guide, why passwords are fundamentally broken against phishing, how the WebAuthn registration and authentication ceremonies use public key cryptography, what the challenge, credential ID, and authenticator data look like on the wire, and why WebAuthn satisfies NIST AAL2 and AAL3 requirements. Identity Expert, powering you to be an expert in identity. Today we're unpacking WebAuthn, the web authentication API, and the broader FIDO2 ecosystem that makes phishing-resistant authentication a browser-native primitive. WebAuthn is a W3C specification that standardizes how web applications use public key cryptography for authentication. Instead of a password that can be phished, leaked, or guessed, WebAuthn uses an asymmetric key pair where the private key never leaves your device. The browser orchestrates everything: registration, signing challenges, verifying that the origin matches. By the end of this video, you'll understand the FIDO2 stack, WebAuthn plus CTAP2, how the registration ceremony creates a credential, how the authentication ceremony verifies it, what roaming versus platform authenticators mean, and how passkeys, the consumer-friendly version of the same spec, enable cloud syncing without weakening the phishing resistance. Let's make asymmetric authentication concrete. Think of a bank that issues each customer a unique padlock and keeps the matching key on file. To authorize a transaction, the bank sends you a box sealed with your padlock. Only you can open it because only you have the key. You open the box, sign the document inside, and send it back. The bank verifies your signature against your public record. Your key never traveled anywhere. It never left your vault. A thief intercepting the sealed box gains nothing without your key. That's the WebAuthn model. The server holds your public key, the padlock specification. Your device holds the private key. Authentication is proving you can sign a fresh challenge from the server. The key never travels. And because each credential is bound to the exact site domain, a fake phishing site requesting the same proof gets a different padlock. The request fails before it can succeed. Passwords have a fundamental structural problem. They must be transmitted to the server to be verified. That transmission is the attack surface. Phishing exploits it directly. The user transmits the password to a site they believe is legitimate. The attacker captures it. Credential stuffing exploits it at scale. One breach exposes millions of passwords tried against every other service. Even bcrypt hash databases can be cracked offline when a server is breached. SMS, OTP, and TOTP codes help, but they're still phishable in real time. A relay attack captures the code before the 30-second window closes. WebAuthn eliminates all of these attack vectors by never transmitting a shared secret. There is no password to phish, no OTP to relay, no credential database to breach. The private key does not leave the device. The signed challenge proves possession, and origin binding means a fake site receives a signed response that is cryptographically useless. It was signed for a different relying party ID. WebAuthn defines two ceremonies, registration and authentication. In registration, the server sends a challenge and its relying party ID, typically the domain name. The browser calls navigator credentials create with these options. The authenticator, a hardware key, a platform TPM, or a passkey provider, generates a new key pair. The private key stays on the authenticator. The public key and an attestation statement return to the browser, which passes them to the server. The server stores the public key and a credential ID. In authentication, the server sends a fresh challenge. The browser calls navigator credentials get. The authenticator looks up the credential by RPID, user verifies if required, PIN or biometric, and signs the challenge with the private key. The signed assertion travels to the server. The server verifies the signature using the stored public key. The critical security property, the authenticator checks that the RPID matches the current origin before signing. This is phishing resistance. A credential registered for bank.com cannot authenticate on fakebank.com. Let's look at the actual WebAuthn data structures. The registration call takes a public key credential creation options object, a challenge, a random byte array, the RP object with id and name, the user object with id and display name, and pub key cred params specifying acceptable algorithms, typically EAS256, ECDSA over P256. The authenticator returns a public key credential containing an attestation object. Inside is the authenticator data, a binary structure with the RPID hash, flags for user presence and user verification, a signature counter, and the public key in COSE format. The authentication call passes a public key credential request options with a challenge and the allow credentials list, the credential IDs the server will accept. The authenticator returns a signature over the concatenation of authenticator data and a hash of the client data JSON. The server verifies. The RPID hash matches, the counter incremented, the signature validates against the stored public key, and the challenge matches what was issued. WebAuthn phishing resistance is its headline property, but it's worth understanding the residual threat model. The primary remaining attack vector is device theft or loss. A stolen hardware key is useless without the PIN, and most authenticators lock or wipe after failed PIN attempts. Platform authenticators on phones or laptops add biometric verification as an additional barrier. For passkeys, synced credentials, the threat model shifts to the cloud account. If an attacker compromises your iCloud or Google account, they could access synced passkeys. Mitigations: strong MFA on the cloud account itself, and the fact that passkey private keys are never directly exposed. Syncing uses secure enclave-to-enclave protocols. A subtler threat is authenticator cloning, particularly for software authenticators. FIDO Alliance certification programs test for clone detection using the signature counter. If the server receives a counter value lower than expected, the credential was used elsewhere. FIDO2 certified hardware authenticators are designed to be physically unclonable. As of 2026, WebAuthn and passkeys have achieved mainstream consumer adoption. All major browsers, operating systems, and cloud platforms support passkey creation and sync. Google, Apple, and Microsoft have launched password manager integrations that store and autofill passkeys. Enterprise FIDO2 deployments use roaming hardware keys for AAL3 compliance under NIST SB 863. The FIDO Alliance has published the Credential Exchange Protocol, a standard for securely migrating passkeys between providers, solving the previous lock-in concern. On the standards front, W3C WebAuthn Level 3 adds hybrid transport, connecting a phone as a roaming authenticator via Bluetooth and QR code, and device-bound versus synced passkey distinctions for high-assurance contexts. The arc of the industry is clear. Passwords are a legacy interface. The phishing-resistant, private key-based model pioneered by FIDO2 is becoming the authentication default. Next on Identity Expert, JSON Web Tokens, the self-contained credential format that powers much of what we've discussed. All primary sources cited in today's guide are listed on screen. You'll find direct links to the RFCs and specifications in the video description below. If this breakdown helped you understand the topic better, please subscribe to Identity Expert. We publish a new protocol deep dive every week. Thanks for watching. If there's a specific identity standard, authentication flow, or security protocol you'd like us to cover next, drop it in the comments below. We build our content based on what the community asks for. Subscribe and hit the bell so you never miss an episode.